So what is the runtime of all of these examples? Let's say we have hypothetical algorithms where the recurrence relations can be described by T of n equals T n over 2 plus n. And then we have a merge sort case where T of n equals 2 times T n over 2 plus n. And then some other imaginary algorithm where the runtime is 4 times T n over 2 plus n. So what the last case would mean is that at each of the recursive levels, you are making 4 recursive function calls on an input size which is split in half. So let's just try to compute the asymptotic runtimes based on the recursive trees. For the case where T of n equals T n over 2 plus n, what you would do is this would be your recursive tree. Your input gets split in half each time, and there's one recursive function call being made at its new level. So if you consider this summation, the runtime for this algorithm is big O of n. Now let's consider the merge sort case where at each recursive call you're making 2 new recursive calls at the next level at an input size which is split in half. And you have log n plus 1 levels, and at each level you're dealing with a runtime of n. So if you sum up the runtime for each of the levels, like you sum up 2 times n over 2 and 4 times n over 4, that each of these levels actually has a runtime of n. So if you do n times log n plus 1, that gives you n log n plus n. So the runtime for merge sort can be considered to be big O of n log n. Now you're faced with another algorithm where the recurrence relation is 4 times T of n over 2 plus n. So you want to add over all log n plus 1 levels the runtime that you're getting. So essentially what's happening is at each recursive function call, you're calling itself 4 times at an input size which is divided in half. So if you solve this summation formula, it shows you that the biggest term is n squared. So therefore the runtime is big O of n squared, i.e. it's quadratic. Now another example that we saw in lecture 3 is Karatsuba integer multiplication. And Karatsuba integer multiplication, as we showed, performs 3 recursive function calls at each level where the input is split in half. So the recurrence relation is 3 times T of n over 2 plus big O of n. And if you solve this gives you a complexity of big O of n to the power of 1.6. So actually this is faster than an algorithm which would be n to the power of 2. Now CLRS describes the master theorem as follows. The master theorem is a theorem which allows us to compute the runtime for recurrence relations quickly based on rules. So first you have to define the runtime of your function as T of n equals alpha times T of n divided by b plus function of n. Now you have to define some relationship between function of n, which is like the housekeeping runtime at its recursive function call, and alpha and b. So basically if you say that n to the power of log base b alpha minus a constant epsilon is an upper bound for the function of n, then in this case you can compute the runtime of the algorithm T as theta of n to the power of log base b alpha. Now if you have the case where your function of n, which is the housekeeping runtime, is equal to theta of n to the power of log base b alpha, then the runtime of your algorithm is theta of n to the power of log base b alpha times log of n. Finally, if you have the case where your function of n is a lower bound, i.e. it's omega of n to the power of log base b alpha plus some constant epsilon, where in both cases epsilon has to be a positive constant, then in that case the runtime of your algorithm t is theta of the function of n. This might look pretty complicated, but actually after you solve some problems with the master theorem, it will all be clarified. For the last case, you also need to evaluate if a condition is satisfied, where alpha times the function on n divided by b is less than or equal to some constant c times f of n, where the constant has to be less than 1. So the master theorem from CLRS might look pretty complicated, but there are many other versions of the master theorem in the literature which might be a little bit more trivial to explain. So for example, let's consider this explanation where the runtime of n equals alpha times the runtime on your input size n divided by b plus the constant runtime for housekeeping is big O of n to the power of d. Now you could say that if the relations between the housekeeping function and alpha and b can be described as alpha equals b to the power of d, then your runtime is described by big theta of n to the power of d times log n. Else if a is less than b to the power of d, then your runtime is theta of n to the power of d. Else if alpha is greater than b to the power of d, then your runtime is theta of n to the power of log base b alpha. So this version of the master theorem is actually equivalent to the version in CLRS, and it can be shown with derivations that it is actually equivalent. So I just find that this description of the master theorem might allow a clearer description of all the cases. So the three parameters that are used in this version are alpha, which is the number of subproblems that you get at each new recursive level, b, which is factor by which the input size shrinks, and d, which is the work that's needed to be done in order to divide the input into all the subproblems and then combine their solutions. Now, if your input size n is odd, then you cannot break it up into two problems of size n over 2, but the master theorem still works, even though your two subproblems would not be of equal size. Like you would need, one would be the floor of n over 2 and the other would be the ceiling of n over 2. You could still apply the master theorem and you could ignore the floors and the ceilings. Now let's just look at the intuition behind all of these cases, and let's look at the more simplified version of the master theorem that I showed you, where you have a constant alpha, constant b, and d, and your runtime of n is described by alpha times t of n divided by b plus big O of n to the power of d. So what do these three cases mean? Consider the trees of these examples. Like you have one recursive function which is t of n over 2 plus n, then your merge sort recursive function, and then some other recurrence relation which is 4 times t of n over 2. So the thing is, for the first recurrence relation where t of n equals t of n over 2 plus n, the relationship between alpha, b, and d is that 1 is less than 2 to the power of 1. And what this implies when you look at the recursive tree is that the amount of work that's done at the top, it significantly exceeds the amount of work that's done at lower levels. This is how you would draw out the recursive tree that's described by this recurrence relation. So essentially what this means is that the runtime is dominated by the amount of work that's done at the top, and time of n equals big O of n. Now for the case where your recurrence relation is 4 times t of n over 2 plus n, the relationship between alpha, b, and d is 4 is greater than 2 to the 1. So the way that the recursive tree looks is that there are many leaves at the bottom, and the total amount of work is dominated by the time to do work at the leaves. And therefore, because the leaves dominate the total amount of work done, the runtime of n is described by big O of n32. Now for the case of merge sort, where t of n equals 2 times t of n over 2 plus n, the relation between a, b, and d is that 2 equals 2 to the 1, so a equals b to the d. So in this case, we have the case where your recursive function calls are being branched out, and the same amount of work is actually done at each level. So you can see that the top recursive function call does work n. The next recursive function calls do work of 2 times n over 2 equals n. So all of those levels actually do the same amount of work. And in this case, the runtime is big O of n log n.